So, we talked about oscillations of several kinds of systems. We showed some experiments also. Now, if an object, material object, if it oscillates, the condition is that you must have some kind of a restoring force, a stable equilibrium, so that when it is displaced from that stable equilibrium, the force brings it back towards that, and then you can have oscillations. In equations, we have this kind of things that we discussed, that you have this restoring force which is proportional to the displacement or whatever parameter this is involved. So, this is a kind of special case which we called SHM, simple harmonic motion, in which the restoring force is proportional to x, and for small oscillations around the stable equilibrium, this will always be the case. If there is no other damping or any other force, it is only this restoring force which is driving the system in oscillations, then you have something like x equal to a cos omega t, constant magnitude oscillations, right. So, this is the differential equations what we call with certain frequency omega, which will depend on the restoring force. This k is here, and which will depends on some property of the system, mass or whatever, moment of inertia, something, some property of the system here. So, the oscillating system property is here, the force property is here, and they will decide the frequency omega. We call it natural frequency of the system. If this system, which includes the object and the restoring force, then that decides that this will oscillate with this particular frequency. Angular frequency, so that difference is there. This omega is called angular frequency. Your frequency will be something like this divided by 2 pi. So, that, but we generally call this also frequency. Then we discussed that together with the restoring force, if you have a damping force also, a dissipative force which consumes energy, then you have some term here. For many cases, this damping force is proportional to the velocity. So, if that be the case, then you have some kind of a decreasing amplitude because of this factor. This frequency also slightly changes. If this damping is small, then the difference is not much. Okay. So, now today we will be adding yet another external force together with the restoring force, together with the damping force. We have yet another, suppose we add yet another external force which itself is periodic, which itself is oscillating. The magnitude of the force, the direction of the force is changing. So, if that force is also an oscillating force with certain frequency, and that is added to this system, then how the system will behave. So, that is the topic of today. So, let me first show some experiments, and then we will discuss more on these equations. So, I have this long straw with me, which has been made by joining several smaller straws together, and then I have this wooden block, and in this block you have some groove, you can see, and I push this end of a straw in the groove here. Now, this is an oscillating system. This is the stable equilibrium position, and then I can oscillate this. It can go on oscillations, and there is some natural frequency of oscillation. There is some restoring force which is bringing it back towards the equilibrium position. Then there is damping, so that the amplitude decreases and finally it comes to rest. Now, what I want to do is to apply an external periodic force on this oscillating system, and for that I will just hold it here and I will give a small angular motion to this block, and just by adjusting the way I am pushing this block this side that side, I will try to make that force periodic with certain frequency. So, watch it. So, here I am and look at my fingers and look at the straw. So, I am going up, I am going down, I am going up, I am going down at a very low frequency, and this straw is also going up and down. Let me do this motion at a very large frequency. Look at my hand, I am shaking my hand with a much greater frequency, and there is some oscillations you can see there. And now I will go with an intermediate frequency and you see what happens. Look at the amplitude of that tip of the straw. Look at this amplitude and look at the amplitude that I am giving at my finger. I am moving my fingers in a very small amplitude, but you see a large amplitude appearing at the other end of the straw. And if I increase my frequency, although I am moving my fingers in a much wider amplitude, larger amplitude, but the frequency is also large, and you see the amplitude of the oscillation of straw tip is much lower. And if I do it at a very low frequency, once again the amplitudes are small, but at that particular frequency, at that particular intermediate frequency, this is that frequency, and you see that a small displacement of finger at the right frequency creates a much larger amplitude of the tip of this straw. So, the kind of oscillations that I showed is called forced oscillation, and that external force, periodic force that I applied, that decides the frequency of that decides the final amplitude of this oscillating system. So, how do I include that in the equations? We have here the basic equation was your mass times acceleration is equal to restoring force. It is not necessarily mass as such in an oscillating system, it could be something else, moment of inertia or some other thing, but something here related to the system, and then this is related to the force as I said earlier. Then you have this damping force, and together with that we are also adding an external force, and that external force you can write as plus some, let us say some f naught cos omega t. Of course, when I am giving this periodic force through my fingers, I am not following that cos omega t type of nice smooth variation, but nevertheless let us say at some frequency omega we are applying an external force. So, what will happen? So, let me remove this part and this part. So, what will be the effect of this part and this part? The effect will be this basic equation is there, this omega corresponds to the restoring force. So, that omega will be there. Let me write it omega naught. So, your omega naught is square root k by m, this restoring force and this system's mass. Together with this you have this another omega coming in, and this is the omega which I can control. If I am applying that periodic force, I can control, I can decide what this omega should be. Then it so turns out that your equations are modified, but finally the x, finally your x turns out to be some constant, which will of course depend on how much is this f naught and how much is this m and how much is this b, times cos of this omega t. This omega t. If this is not there, if damping is also not there, then your x is some other constant, let us say b, some cos of omega naught t. This omega naught is that square root of k by m. So, this is the natural frequency. But if the periodic external force is there apart from this restoring force and some damping is there, you again have a periodic motion, but then the frequency is omega, this frequency. So, it is the forcing frequency that decides the frequency of oscillation. And what is this amplitude A? This amplitude A depends on relation between this omega and this omega naught. And if omega is close to omega naught, this A is large. And if omega and omega naught are widely different from each other, then this amplitude is small. This phenomena is known as resonance. So, when these frequencies match, you have large amplitudes. So, that is what I was doing. My frequency of variation of the finger, displacement of the finger, I was trying to adjust with the natural frequency of that straw system, and if that happened, the amplitude was large, and if this frequency is very low or very high, the amplitude was small. So, I will just show some more examples of resonance, and you enjoy these experiments. So, I have this head massager. It has several these metallic rods, and then on top of that these beads are there, and they are of two different lengths. So, I can see 2, 4, 6. 6 are of one length, and then these 3 and plus these 3, 6 are of larger lengths. If I hold it here and vibrate one of them, they are all joined together here. So, if I vibrate one of them like this, what will happen? This base to which this is attached, that will also experience some force or some small vibrations or oscillations or something, some disturbance there. And since all the others, these rods are connected to the same base, for each of them that base will act as an external source of extra vibrations. Because if I am vibrating this, then all others will feel this periodic force through their joints at the base. Now, the different lengths correspond to different frequencies. Just I will show that. Just think of these two. If I pull this one apart, this one, look at the frequency, and if it is this one, it is a different frequency. This frequency is larger and this frequency is smaller. So, each length corresponds to a particular frequency. Now, let me pull this longer one and you see what happens to the other these rods. Which one are oscillating and which one are not responding or responding with such a small amplitude that you cannot see. So, if I oscillate the longer one, only the other 5 longer ones they oscillate with sizable good amplitude, and the shorter ones are just stationary. Whereas, if I oscillate one of the shorter arms, see what happens. The longer ones are just staying almost at rest, and the shorter one are oscillating with sizable amplitudes. Okay. So, if the frequencies are close, like this one, the frequencies are same. So, if I vibrate this external frequency, and this vibrates at its natural frequency, and they match. Same thing happens when I start with the smaller one. So, you are already familiar with this apparatus. We did experiment with this apparatus to show that Faraday's law of induction, where if I change a magnetic field, induced electric field is created, drives a current, that current exerts force on this other magnet which is hanging. Now, the same experiment I will repeat, but this time our focus is on the frequency of this external force on the magnet. Magnet is the oscillating system. This spring is providing the restoring force. Of course, gravity is also there, and because of that it can vibrate at certain natural frequency. This is the natural frequency. And if I pass a current in this solenoid, and if that current is varied at a particular frequency, then the magnetic field will also vary with that same frequency, and whatever force acts on this magnet because of that magnetic field will also be at that frequency. So, that will be the external periodic force. So, I take this magnet and put it here and oscillate it here at certain frequency, and that frequency will decide the frequency of the external periodic force. So, you focus on this frequency at which I am taking it in and out, and the amplitude of the oscillation here. So, look at it. I am going with a very small frequency. It is a periodic force that I am applying, but then the frequency is quite small. I go at a very large frequency. And you see it hardly oscillates, the magnet hardly oscillates, and now I am going with the intermediate frequency. And you see the amplitude of the oscillation. The magnet is now oscillating with a much larger amplitude, whereas if I decrease the frequency, the amplitude goes down. If I increase the frequency too much, amplitude goes down. But if I keep the frequency somewhere here, the oscillation amplitudes are maximum. So, this is resonance. This is resonance. So, in the previous lecture, I showed you an equivalent, mathematically equivalent system in terms of an electrical circuit. You have something which oscillates in a mechanical system, but in electrical system, electrical circuit, current can oscillate. And in that lecture I told you that if you have a capacitor and an inductor and you connect that, there is a natural frequency which is 1 by square root of L into C. Some damping is always there, some resistance is always there. So, in the circuit you have some resistance, and then if I put an external power supply here, AC power supply, that plays the role of this external periodic force in mechanical system. So, if you connect this type of system where you have an inductor, where you have a capacitor, where you have a resistance and an external AC power supply, you are actually making a mathematical equivalence of this forced oscillations. What will be the equation? The equations will be your L di dt, which is minus q by c. This is the basic oscillation system. The natural frequency is decided by L and C, and then you have this damping or dissipative term R times I, and now you have an extra this E. So, I can write some E naught cos of omega t. So, this is that external force which we are using, or you can put a plus sign, does not matter, I am not writing the phase. So, this is that external thing. So, this omega is now frequency of the external power that we are feeding. External power source, whatever we are adding to the circuit. And from this system you have a natural frequency omega naught, which is square root of 1 by LC. And if this frequency omega and this natural frequency omega naught, if they are close to each other, then the current in this circuit will be high. And if these are widely apart, this omega here and this omega naught here, if they are quite different from each other, then the current will be, amplitude of that oscillating current will be very, very low. This is used in all kinds of tuning circuits where of the many frequencies available, you only want one particular frequency to drive your circuit. So, then you tune your natural frequency omega naught, add that particular frequency, your desired frequency. So, only that particular frequency, that component will provide you the real current and in the circuit. So, that is how the tuning circuits are made. You may be wondering, I talked so much of oscillations and oscillating systems, but I did not really work with simple pendulum. I showed it once, but I did not really go for its mathematics and all that. Simple pendulum is of course your very familiar object. You must have done experiments in your schools. Now, it is called simple pendulum, but it is not really simple. There are many things to learn from that simple pendulum, and that is why I have reserved it for full lectures on simple pendulum that will be coming next. You will have to do some angular motion revision. When you have a pendulum and the bob oscillates, essentially it is the angle from the vertical that changes. So, you have angular displacement, and then you will have angular velocity. If you call the displacement as theta, then the velocity, angular velocity will be d theta dt, rate of change of theta, and rate of change of angular velocity will be d2 theta dt square. On the other side, where you have this mass times acceleration, this side you will have moment of inertia, which is some mass times distance square from the axis of rotation, and in place of this acceleration you will have angular acceleration, and then here in place of this restoring force you will have torque of the gravitational force. All these mathematics we will do in the next lecture.